right, two more types of deposits. First off, sedimentary deposits. Remember, sedimentary processes are when material settles as sediment and forms kind of layers. A little bit different than that, the magmatic layered settling. That was more cooling of crystals in magma. This is a little bit different. So chemical sedimentation is where minerals are concentrated and precipitated directly out of lake or sea water. All right, so surface water. So you get evaporate deposits. So you have a lake or shallow area of the sea, maybe kind of cut off a little bit. There's stuff in there. Salt, halite, gypsum, borax, sylvite, a number of different things. So you have these minerals kind of all in this water. And as the water begins to evaporate, that material that's dissolved in there begins to settle out, concentrate and settle out, forming these layers of different material. Also, different type of sedimentary deposit that we'll talk about that we can extract material from are banded iron formations. This goes back to kind of way early on, again in the beginnings of Earth. So you have ocean water. This is really before much life. The only thing that really existed were kind of early sea organisms, bacteria. But the ocean was filled with molecular iron, not big chunks of metal iron, but just molecularly there's iron floating around. You have these very early sea organisms like bacteria and algae, which are kind of plant-based, and they take in carbon dioxide and energy from the sun, and they produce oxygen. Plants produce oxygen. But these things that are floating around in the ocean, algae, they're producing oxygen. Well, the oxygen they're producing, instead of making their way into the atmosphere, they actually get trapped in the seawater with the iron, and you take iron and oxygen, and when you mix the two, you get rust. All right, so this material this rusty iron material began to form and settle at the bottom of the ocean, creating these things called banded iron formations, where we can mine out now iron. So here's a great example of an evaporate deposit. Looks like a very dry area, so any kind of rain, moisture that falls in the area looks like it makes its way to this location. And as that water evaporates, it leaves behind material. So this whitish material here, I'm not really I don't really know exactly what this is. It could be halite, salt. It could be gypsum, which we use for kind of drywall. So, but in any case, this material is there. As the water evaporates, anything that's in that water will kind of settle out. Have you ever put a pot of water on the stove, turned it on, and it's boiling, and you forget about it, and you go back, there's no water left, but there's this kind of white stuff? There's this white stuff that's in the pot. That was in the water. So that was the minerals that were in the water. The water evaporated, it left behind those minerals. Oftentimes at our homes, that's calcium and maybe some other things that are naturally just in the water. But kind of the same process. So whether it's a shallow lake or a shallow area of the ocean that's maybe cut off a little bit, some sort of barrier, maybe at high tide water comes in, or during a storm water gets pushed into these areas, but as the ocean recedes it gets cut off, so you have this shallow basin, very salty water. It evaporates away, the salt kind of settles out, salt, gypsum, or whatever type of minerals are there. And then banded iron formations, they look like bands of rust. So you see these rusty layers. So this banded iron formation, again, formed early on in Earth. Really iron-rich water. Once the oxygen from some of those producers was created in the ocean, that molecular oxygen bonded to the iron to create solid iron oxide, rust, and it settled down to the bottom of the ocean. So now, looking at this area, it looks very dry, looks very deserty. So there's no oceans there now, but again, billions of years ago, this was the bottom of the ocean. Plate tectonics moves things around. Just because it's a desert now, it doesn't mean a billion years ago that's what it was. So here are some old banded iron formations that can be found around the world. The major ones, the only major one in the U.S., up near kind of Minnesota, Wisconsin area, we have a banded iron formation. And in fact, 75% of all the iron mined in the U.S. comes from these banded iron formations. You mine it out, you crush it up, you molecularly extract the iron, you do some chemical processes to it to get that iron out. This looks like, I'm guessing this is probably Australia somewhere. Again, another look at how that works. So you get iron floating around the ocean, mixing with that oxygen that's produced from algae via photosynthesis. These are little microscopic plants floating in the ocean. Creates iron oxide. That material sinks to the floor and kind of builds up. Yeah, so you can read a little bit more about it, but that's essentially how it works. All right. Placer deposits. We have sedimentary deposits and placer deposits are the last two areas in which minerals can get deposited that we would mine out. So when minerals are concentrated in streams, rivers, and beaches, they are called placer deposits. I should say not only in, but in or around streams, rivers, and beaches. When the velocity of water slows down, if it's carrying anything, heavy minerals are typically deposited. Think gold, platinum, gems like zircon or diamonds. Other gemstones, other materials can be found in placer deposits. The California gold rush. When most people think of mining for gold, they think of like old miners in a stream with a pan of gold, like shaking this pan of stuff looking for gold. That's placer mining. They are digging through stream or river sediment to look for, in this case, gold. So the California gold rush in 1849 began with the discovery of rich placer deposits of gold in streams draining the Sierra Nevada mountains. Now, the gold originally formed in hydrothermal veins, that hydrothermal process, but it was eroded and carried in streams where it was deposited in placer deposits. So originally, in California, on the coast, boundaries, a lot of stuff going on there. So it was formed hydrothermally, porphyry deposits, or VMS deposits, but that material was weathered and eroded down over millions of years, made its way and got trapped in streams. Something interesting to note. So this was kind of headquartered, the California Gold Rush kind of headquartered out of San Francisco. The San Francisco football team is known as the San Francisco 49ers. The 49ers got their name from all the people that created the gold rush in 1849. If you were a 49er, you were someone that came to California in 1849 looking for gold. Hence, the 49ers, hence the San Francisco 49ers. That's where they got their name from, due to the gold rush. So again, maybe there's some hydrothermal veins that contain gold, a number of other things, but over time that material was weathered, broken down, and eroded, moved, and deposited into streams. Now, placer mining can be done in or near streams, and when I say in, I mean kind of touching or near streams. Streams, rivers, they move around. So where a river is now wasn't where the river was 100 years ago or 1,000 years ago. So when you're doing placer mining, not only are you looking kind of in and around streams, but also maybe kind of adjacent to, next to, maybe where the stream once was. 1,000 years ago, 5,000 years ago, 20,000 years ago, because there could still be gold deposited in that sediment where the river once was. So if you're in a stream, again, it's where the water slows down, and that tends to be on the inside of curves. On the inside of curves, right? On the inside of the curve of the stream, on the inside of the curve. So if you know there was a curve where the stream maybe once was, thousands of years ago, you can follow that track. You can follow that track. So water, just by the sheer physics of how things work, it moves faster on the outside of the curve, but it moves slower on the inside of the curve. So where water slows down, material will be deposited. So if you ever find yourself in a shallow stream searching for gold, look at the inside curve. Look at that inside curve called the point bar. Point bar. So here, this is probably up in Alaska. This is an old dredge that would mine out sediment looking for gold along this ancient stream here, or along this current stream here. but looking at all this sediment. So not only would you want to look, obviously, in this area, but maybe even around, maybe even off into the woods here, because the river could have been there at one point. So here's another great example. I think in the background here, you can see where the river, looks like where the river is. I can see kind of some river back here, but all of this is large-scale placer mining. This is maybe where the stream once was. Or this is where that river once was, so they're kind of mining out this ancient channel looking for gold. These are the 10 counties in the U.S. that have the highest concentration of gold-related placer mining claims in the U.S. Obviously, you can see a good amount of them are in California, some in a couple in Oregon, one in Idaho, one in Colorado, and then in Arizona. So if you're looking for gold in Arizona, typically Yavapai County is what you're looking for. It's kind of north of us. It's kind of north. That's like Prescott area. That's Yavapai County. Good luck. But, I mean, good luck finding any. But that's where you'll find it. Or the best bet. So, kind of think about all of these. Magmatic processes, hydrothermal processes, sediment, porphyry. This is typically where you can find these things as it relates to boundaries. Not always, just typically. So, when we're looking at, igneous magmatic intrusions, typically at continental or convergent boundaries, so pegmatites, kimberlites, porphyry deposits, more closely associated with convergent boundaries because you get a lot of magma produced. Sedimentary deposits, that can typically actually happen anywhere. Layered settling, again, magmatic processes, typically that can happen anywhere, but you think of large-scale magma bodies that can be intruded up, but don't really go anywhere underneath oceanic crust, so kind of away from boundaries. Maybe some sort of large mantle convection plume kind of coming up. And then VMSs, I know it's kind of hard to see. Typically divergent boundaries, but they can be found elsewhere because there is also magmatic processes happening at convergent boundaries. So anyway, again, typically you would find these at these locations, but it's not always the case. You can find VMSs near convergent boundaries, layered settling at convergent boundaries, sedimentary deposits near convergent boundaries because they can typically happen anywhere just where material is deposited. So, it just really depends on what it is you're looking for. But there's something special with, convergent boundaries versus divergent boundaries. Again, with convergent boundaries, typically you're creating cracks for material to move around and be deposited. All right. We'll go ahead and pause there. So we've talked about, well, how does this stuff get into the crust where it's at? Now we'll talk about, well, how do we mine it out? Now that it's there, how do we pull it out of the ground? So that's what we'll talk about in section 3. See you in a second.